Everybody, please, where's the public address system? Baba, start. You are live already.
Okay. Okay, good morning, class. This morning we are going to be considering two topics, although we started last week, but we are going to restart all over again. That's energy and chemical reaction, and then the rate of chemical reaction. The rate of chemical reaction. So, the first thing we are going to go on through is the law of conservation of energy, as it is integral to this particular topic. I might ask you that what is energy? But that is not a question pertaining to what we are doing here. That is for physics. But there are two basic laws of conservation of energy, while the first one there is the law of conservation of energy. What does that state? What does law of conservation of energy state? It naturally, even without human interference. Again, it is the natural interaction of any form of energy. Without human interference, all form of energy have the tendency of being converted to form. And that is the reason why you see the entire solar system. When I mean the entire solar system, I'm talking about the sun and the 9 planets interacting together in such a way that the energy, which is the solar energy, converted to its form. So, also in chemical reactions, the interaction that we are actually going to be studying there is the form of heat. And that is why we say that energy and chemical reaction, so we can simply say heat and chemical reaction. Heat and what? Heat and what? I want people at the back to respond. Heat and what? Okay, heat and chemical reaction. So what do we call the kind of heat that is associated with chemical reactions? That is what we regard as enthalpy. Everybody say that. Everybody say that? Enthalpy. And enthalpy is actually a state function. It is a what? It is a state function. This particular induction will make sense to you by the time we progress in this particular topic. We are talking about that enthalpy is a state function in that it is independent of any form of pathway. Rather, it is a state that interacts with both initial and the final form. Both what? Initial and the final form. Both initial and the final form. So what is now what we call enthalpy of a reaction? What do we mean by enthalpy of what? Reaction. I've said it, but let's define it all over again. Enthalpy of reaction simply talk about heat associated with a particular chemical reaction. Heat associated with what? A chemical reaction. The reason why I'm making emphasis on a chemical reaction there is because we are in chemistry. But also this particular heat can be associated with physical changes too. So when we're talking about it, we are talking about it both in physical and chemical changes.
Hello everybody. Can you all hear me? Can you all hear me? Now in the next 1 minute, listen and listen very well. In the next 1 minute, when you check your platform, that is the general student platform, you are going to find a little video. Now share it now. Every friend of yours that is in need of it, we have to pass. Do it on time. Hello, please, hi.
No. Air condition.
Oh yeah, hello, be fast.
For where? Also.
Just as they are telling you, they just tell them that this land is formed now, so that they can join. Some of them are at home. So, Baba, in the next 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Continue, sir.
Okay. Okay, I was talking about entropy of reaction. We're talking about entropy of reaction. We're talking about energy associated with a chemical reaction. Energy what? Energy associated with the chemical reaction. At the beginning of a particular reaction, there is a particular energy, which is the state function of the chemicals involved. There is a particular energy associated with the chemicals that are involved in the beginning of the reaction, even before the reaction proceeds. That particular heat, that kind of heat of reaction, is the heat of the reactant. Is the what? Heat of reactant. And that we can represent as HR. So at the final point, when the reaction must have proceed to the very end, there is another heat associated with the chemicals involved, which we call the what? Heat of what? Heat of product. And that is HP. It is the function of this particular two forms of heat that we actually use in determining what has happened to heat form in course of the reaction. Either from the environment heat has been taken in, or from the system it has been given off to the what? Environment. And that is what differentiates two forms of reaction in terms of association with heat. And that is where we have endothermic and what? Endothermic and what? And exothermic reaction. So what do we know as endothermic reaction? From the word endo, endo means inward. Yes or no? Yes or no? Even from people who are offering biology, endoparasite. If you are what we call offering physics, you have seen what we call endogonic reaction and so on. All this is talking about inward. And thermal, which means what? Heat. That means in this form of reaction, heat is absorbed from the environment into the what? System. It is what? It is absorbed from the environment into the system. And in such way, the heat of product for endothermic reaction now, the heat of product, if it is absorbed, that means the heat of product will be greater than the what? Heat of what? Because what started it, their heat, they have a particular form of energy that associated with them. Yes or no? Now absorbing more energy in, what will happen? their energy will what? Increase. Their energy will what? So in that we say that the heat of product is greater than heat of what? Reactant. Such a way that energy change in this particular reaction, change in energy, which is represented by delta H, is simply heat of product minus heat of reactant. This formula is irrespective of any form of reaction. It is what? Heat of product minus what? Heat of what? Reactant. Such a way that in endothermic reaction we have heat of product greater than heat of reactant, so that change in it will be equal to what? Positive sign. Why? Because what we are subtracting heat of reactant from is greater than the heat of what? Reactant. You understand what I'm saying now? Do you understand that?
Yes, sir.
If you have any question you can ask before we move on. Okay. Without any question, we can move on to exothermic what? Reaction. What are exothermic reaction? It's just opposite of what we've defined there. So what is that? We are simply talking about what? Chorus? Yes? Heat is what? Giving off to the surround. That means at the initial point, there is a particular heat that's associated with that particular reactant, yes or no? And if they lose heat, that means they lose energy to the environment. What will happen to the heat of product? At that particular point in exothermic reaction, we have heat of reactant greater than what? Heat of what? Product. Yes or no? Or we say that heat of product is less than what? Heat of what? Reactant. And at that particular point, looking at changing heat, it will now be what? HP minus HR. Knowing that this one is lesser than this one will give us what? A negative what? Value. What are the various examples of changes that are endothermic changes? What are the various examples that you know? I gave you some last week. Yes? Speak up. Endothermic reaction. Endothermic reaction. Thermal catalyzed reaction. Number one, thermal catalyzed reaction, have you? E.g., what are example of thermal catalyzed reaction? Thermal decomposition. Thermal dissociation, right? Yes. Second one is what? Action of light. And other light catalyzed reaction. E.g., photosynthesis. Action of what? Of light on what? On silver bromide. Yes. Ones? Okay, and silver bromide in photographic plate. Yes. Another one? Huh? That's all right. Okay. We have more of this. When we get to organic chemistry, you know of one more, which we call the halogenation of alkanes. Halogenation of alkanes. How many of you understand what we call halogenation of alkane? Like the chlorination of methane under UV light by the use of what? UV light as catalyst, where you have the formation of your tetrachloromethane. Yes or no?
Yes.
Okay. So, what are examples of exothermic reaction?
Combustion of
Understand? What are examples of exothermic reaction? Combustion and what? Anodization of metal. Anodizative processes. Yes or no? Okay. What are examples of oxidative processes? Respiration. Yes. Corrosion of metals. Yes. That's all right. We have more. Any form of combustion processes that you say that addition of oxygen to so like combustion of a particular compound to give like combustion of organic compounds now is an exothermic reaction. Do you give another example? Is that all? Neutralization of what? Neutralization of acid and base. They are all examples of what? Exothermic reactions. They are all examples of what? Exothermic reactions. Any question before we move on? Yes? What do you say? The putrefaction process. We are talking about decay. And you said that oxygen is that's what I'm saying. I don't understand what is oxygen released during the what is released during the decay process? Hydrogen sulfide, methane, yes, which other things? Carbon 4 oxide, CO2. Yes. Are you gonna say now? CO2.
Do you understand?
So you don't say that in what do you call it, in decay process the oxygen is released to the environment. Am I missing anything there? Where did you get that from? No, talk. You are here with me now. Okay, that's what I'm saying. That's a physical change, right? Okay. When you have decay process, it's breaking down. Yes or no? Breaking down of what? Bonds, Sabi? Yes or no? Breaking down of things. And whenever there is breaking down, what usually happen to it on most occasions? When if a bond is broken down, if a bond is broken down, it will be released. If there is formation of bond, listen to me. If bond formation is greater than what do you call it, bond breaking down, such reaction is expected to be exothermic. I get what I'm saying now? Bond formation is greater than what? Than what?
Breaking down.
If bond formation is greater than what? Bond breaking down. Do you get the concept now? So that is it. So when I say that decay now, decay is not breaking down bond. So that is it. Do you get the concept? Are you with me? Okay, very good. Okay, now let's move on. Anybody with another question? Anybody with another process? Another question? Any question, please? Any question? Okay. So let's move on. Out of this, we have different form of reactions and their enthalpy that is associated with them, and that is what we want to go on into. We want to look at types of chemical reaction and the heat associated with them based on the name of that particular chemical reaction. Are you get what I'm saying now? Yeah. So the heat of chemical reaction, please get me duster, please. I'm going to end the class with the phase, what do you call it? With the phase diagram, talking about the graphical representation of exothermic and endothermic reaction. I mean to end this particular topic one. Okay, for enthalpy of reaction, we have different form of reactions, like we have heat associated with formation process, with the formation reaction where new bonds are being formed. I get what I'm saying now? Where two substances combine together to form a single unit. I get what I'm saying now? So heat of formation, we usually represent this one by HF, and in terms of standard, just to differentiate it from standard heat generally usually carry this, the theta, and so if it is heat of formation, it will be what? HF theta. What do we mean by standard heat? In standard heat is made in reference to 1 mole of a substance. It's made in reference to what? 1 mole of a substance. It's made in reference to 1 mole of a substance. So when we are talking about heat of formation, we are talking about what is being formed is what we make reference to the 1 mole. I get what I'm saying now? That means heat that is involved when 1 mole of a substance is being formed during a chemical reaction. When 1 mole of a substance is being what? Formed during a what? Chemical reaction. So what is heat of formation? Heat associated with what? Formation of a substance. Heat associated with the formation of what? A substance. While standard heat of formation is simply talking about heat associated with what? Formation of 1 mole of that what? Substance under standard conditions. Under what? What are the standard conditions? STP, that means standard temperature and what? Standard what? Standard temperature and pressure. Example, for 1 mole of H2O to be formed, the reaction comes from hydrogen, which is gas, plus oxygen, which is another gas. But we know fully well that what we are having there is not up to what? To oxygen, and we have 2 oxygen atom here. Yes or no? A one molecule. Yes or no? So we place what? Half here. So this one here can be gas, can be liquid, depending on if it has been condensed. Do you understand what I'm saying now? So at that particular point, the heat associated with the formation of 1 mole of water from its constituent atoms, I get what I'm saying now, is what we call the heat of formation of what? Water. It's what we call the heat of formation of what? Water. And in this kind of place, what we have for heat of formation there? Will it be positive or negative? For heat change. Will it be positive or negative? It will be what? Will it be positive or negative?
I'm serious.
Will it be positive or negative? Why is it negative? Why is it negative? You should be able to give me the reason here now. Why is it negative? Because what? No, even without that, I'm talking given as example today under exothermic and endothermic reaction. Why is it negative? Because it's a combustion process. Is this not a combustion process? So you cannot easily recognize that this is a combustion process again.
Are you okay?
This is a combustion process. So this particular heat associated with this reaction will be what? Negative. Do you get what I'm saying now? Are you with me? Okay. So that is heat of formation. So we can go on to the next one. Okay. Heat of solution. Heat of solution. Are you with me? Are you with me for heat of solution? Can we move on? So what's heat of solution? What's this of solution? Heat of solution, please. Water as a universal solvent. What's heat of solution? This is the heat associated. That is, when I say heat associated, I mean heat given off or what? Absorbed. Heat what? Given off or what? Heat given off or absorbed. So it depends on the condition. Depends on what kind of reaction it is. Are you getting what I'm saying now? So this is the heat involved when a substance called solute is dissolved in a solvent. When a substance called solute is dissolved in another substance called what? Solvent. I get what I'm saying now. So when we are now talking about standard heat of solution, we're talking about standard heat of solution. We are simply talking about heat involved when 1 mole of a solute is completely dissolved in a solvent at a standard, under what standard what? Condition. Under standard condition. What's your name? You. What's your name? Yes? Yes. You. Yeah. Tumise. Okay. Whatever it is, can you tell me what standard condition is? What standard condition? Your mind is not here. Because your mind is here, you will not tell me that you will not be thinking of this. What standard condition, everybody? What is standard condition? Standard temperature and what? Standard temperature and, if you don't know that before now, standard temperature is simply 0 degrees Celsius, which is equivalent to 273 Kelvin. Are you what I'm saying now? While standard pressure is 760 mmHg, or what we regard as 180 or in Pascal, which is what 1.013 times 10 raised power what 5 what Pascal. And this Pascal is same thing as what Pascal is equivalent to what Newton per what meter square. Do you get that now? So all this, so that when you see this, you know fully well that we are talking about standard condition, standard temperature and pressure. When 1 mole of a substance is completely dissolved in a what? Solvent, the heat that is involved is the standard heat of what? Solution. Is the standard heat of what? Solution. Can we move on? Any question before we move on? Any question? No? Okay, let's look at the next one. Number 3, heat of neutralization. Heat of neutralization. Standard heat of neutralization, N or capital N, any how you want to represent it. It's represent what? Heat of what? Neutralization. What is heat of neutralization? Yes. Heat associated, yes. When what? When an acid reacts with base. Is it when an acid reacts with base? An acid can react with base and neutralization might not be complete. Yes or no? Yes or no? Yeah. That means that neutralization is not yet done. Yes or no? When it's partially done, it's not yet done. Do you get the concept now? But we are talking about when complete neutralization occurs. So it involves when what? An acid is completely neutralized by base, or a base is completely what? Neutralized by acid. And remember our identity of acid and base. What are the identities of acid and base? What are the identities of acid and base? H plus acid, and what? OH minus, which is what? Base. So according to others protocol pattern, we can talk about proton donor and proton acceptor for base. And in terms of electron acceptor and electron pair donor. Yes or no? Yes. Electron pair donor, electron pair acceptor. Do you get the concept now? So in that, when we are talking about H plus and OH now, we are talking about H plus OH minus to give what? H2O. Yes or no? This is liquid. This is what? Aqueous, because they are ions. Yes or no? Aqueous. Yes or no? So in this, look at what we have in there. That is hydrogen ion combined with OH ion, which is hydroxyl ion, to form what? Water. 1 mole of what? Water. Yes or no? Yeah. So we are simply talking about it involved when hydroxyl ion completely neutralize what? Hydrogen what? Ion to form what? 1 mole of what? Water. To form 1 mole of water. Heat involved at that particular time is the standard heat of what? Neutralizing. Standard heat of what? Neutralizing under standard condition. Under standard condition. When you are defining heat, standard heat, make sure that 1 mole of the substance is actually being made mention of. Standard condition must be made mention of. Either you place under standard condition or you say that at what? Standard temperature and pressure. Or let us say you can put it as what? At STP. Nobody will say that they don't understand what you mean by STP, except it's not the person is not what do you call it? A chemist. So the person is not actually doing anything on chemistry at all. The person is just giving marking guide and say, I don't understand what STP means. Are you get what I'm saying now? So at yes, standard heat. Okay, when you are talking about standard heat, you must make mention of 1 mole of the substance involved. I get what I'm saying now, and also standard condition. It involves when 1 mole of a substance either form, dissolve, or anything that happens, or any kind of reaction. Abi, you understand it now? Under what? Standard condition. Under standard condition. So, yes. Yes. Normally, it might not be under standard condition. It's not a must. It must be under standard conditions. If it is not under standard condition, another heat will be associated with it. That particular is just the heat involved. And at that particular point, you can make reference to your Boy's Charles law, gas laws, or any form of other laws to actually bring it back to what will eventually happen under standard conditions. Because standard conditions have been referenced under this. You can use what do you call the molar volume of gas to actually determine a lot of things. Abi? Yes or no? So other formulas can come in for you to resolve it back to what? Standard condition. And that is one of the major things that we're being asked from you in your examination. They don't ask straightforward question applied, that you must be able to make reference to standard condition when you are to bring them back to normal, especially for gases. Do you get it now? Do you get that? Are you with me? Okay. So that is heat of neutralization. Number 4, we have heat of combustion. Heat of what? Heat of combustion. So what is heat of combustion? What is heat of combustion? The heat that is involved in combusting what? A substance. Yes or no? What's combustion? Combination with what? Combination with what? Oxygen. When you're talking about combustion, you don't talk about any other thing. We're talking about combination with oxygen, and it's usually been accompanied on most occasions by what? Flame. By what? Flame. I think we know what you mean by flame, right? Flame. When you're talking about flame, you're talking about fire. Are you get what I'm saying now? It's being accompanied by flame. Either colorless flame or colored what? Flame, depending on the substance that is being combusted. Yes or no? What are examples of substance that burn with colorless flame? No, be bold. Say it. It's what? Hydrogen burns with colorless flame. We have done this in class now. So you want to say it and you are keeping quiet. So when you get to examination now, when you see answer, you now say that I'm not sure. So because of that, you not pick that answer again. You now leave it empty, blank. No. Okay. So now when we are talking about this, we're talking about AC. As you can see now, then in standard heat form it can be this, which means what? It's a standard, under standard what? Condition, and for 1 mole of that particular substance. That means heat involved for what? 1 mole of a substance to be completely what? Combust. Combusted, 1 mole of a substance will be completely combusted under standard condition. That heat associated, and we all know fully well that this is an exothermic reaction. Yes or no? So in that we can change it from heat associated. Now we can say that the heat liberated, because we are so sure of what will happen. Yes or no? Heat what? Liberated. So also in neutralization we can say heat what? Liberated. But in solution, the solution can be exothermic and it can be endothermic. Yes or no? Depending on the substance you are what? Dissolving. Depending on the substance you are dissolving. If you are dissolving an acid, you are dissolving a base, you are expecting a what? Exothermic reaction. You are dissolving certain salt is what? Endothermic what? Reaction, because it's only breaking bond and they are not forming anything. You get it now? So that's why we say heat associated. I mean, heat liberated or absorbed. So in order to avoid that long statement, now we say that heat associated. Yes or no? Do you get that now? Do you get that now? Okay, very good. So now let's go on to the other part. Can I clean this side? Are you done with this side? So depending on the kind of reactions, there are lots of reactions that we can make reference to. Either decomposition and so on and so forth. So all heat associated with them, we can talk about that one. But what I would like us to go into is what we call bond angle, bond energy. Sorry. That's under hybridization, the shape of molecule. Yes. Formula of combustion. Formula of combustion. Heat of combustion. Yes, now this is standard heat of combustion. This is standard heat of what? This is ordinary heat of combustion. Are you talking about changing it? I'm giving this one from the beginning now. Repeating now, this one is still the same. But when we talk about bond now, maybe bond energy now, we can now start talking about another formula. As you can see now, this is simply heat of product minus heat of what? Reactant. And we all know that in this one will be lesser than what? This. Yes or no? So that is why it will be what? Negative. And that's why it's an exothermic reaction. Do you get that now? Another question before we move on? Another question before we move on, please? Okay. Bond energy. What do you mean by bond energy? What do you mean by bond energy? Speak up. What's bond energy? What's bond energy? Okay, now right. Bond energy is the energy associated with the force of attraction energy associated with the force of attraction between atoms in a compound. Esther. Between atoms in a compound. Atoms in a compound. It is actually the energy that is associated with covalent bonds, because that's where we can easily calculate it. With covalent bonds between atoms in a what? Compound. Atoms in a what? Compound. So what are we saying? For us to actually calculate for reactants, there is a bond energy between reactants. Yes or no? Yes or no? So that means the bond energy of the reactant, and then that one of what do you call it? The product. We have bond energy of what? The product. This one is not BPO. So bond energy of the what? Product. Such a way that if these particular ones are to go on to product, they release a particular heat, yes or no? Or they absorb a particular heat, yes or no? Why these ones, they are going to go back to reactant, they are going to absorb a what? A particular what? Yes or no? So the calculation for change in energy using bond energy calculation is simply the heat associated with the reactant, or the bond associated with reactant, minus the heat associated with what? Product. So we can simply say, I do like to put it this way, Br minus what? Br minus what? Bp. Can you see that this one is different a bit from what we have initially here? Yes or no? Because we are talking about bond what? Energy. We're talking about what? Bond energy. Now, in bonding, in what do you call it? In products or reactant going down to product, there is a certain amount of energy that is associated with the breaking down of bond, and there's a particular amount of energy that's associated with what? The formation of what? New bond. Do you get what I'm saying now? Formation of what? New bond. For the reactants to react, the bond between the molecule of the compound involved must be what? Dissolved. That means it must be broken down. Then after breaking down, these particular ones will now recombine to form the what? The product. Yes or no? They will now recombine to form what? The product. So bond breaking minus bond what? Form. So Br minus what? Bp. So this particular for covalent bonding, there is a particular energy that is associated with every form of covalent bonding. So let me give you that. Maybe you can just write. You will just write Now let's look at this one. You start from number 1. Okay, right? C to H bond. Where's the marker? C to H bond this way, okay, right? So you follow that particular pattern when I make mention of things. C to H bond. Under this place, write 413. 413 kilojoule per mole. 413 kilojoule per mole. Kilojoule per mole. Kj mol raised to power -1 or kj slash what? Mol. C to C, CC, C to C single bond. C to C single bond. C to C single bond. This is C to C single bond now. We can have triple bond, double bond like this. C to C single bond. 348. 348. C to O double bond, that is carbon to oxygen. C to O single bond. 358. 358. C to N single bond. 305. C to N single bond. 305. Are you there? That means carbon to nitrogen single bond. 305. C to F single bond, that means carbon to fluorine. 485. 485. Are you there? And online viewers, please try and follow up. C to Cl, that means carbon to chlorine single bond. Carbon to chlorine. 339. 339. Carbon to chlorine. 339. Then carbon to bromine. That means C to Br single bond. 276. 276. C to I. C to I, that means carbon to iodine. 240. 240. Carbon to sulfur single bond. Carbon to sulfur, single bond. Are you there? 259. 259. Then hydrogen to hydrogen, single bond. Hydrogen to hydrogen, single bond. 436. 436. Then C to C double bond. C to C double bond. 614. 614. C to C double bond. 614. C to C triple bond. 839. C to C triple bond. 839. What do you mean by triple bond? I think you understand that.
Yes, sir.
Ife? What happened? Okay. Are you there? 839. C to O double bond, that is carbon to oxygen double bond. 745. 745. 745. 745. Then C to N double bond, carbon to nitrogen double bond. 615. 615. Carbon to nitrogen triple bond. Carbon to nitrogen triple bond. 891. 891. Now, nitrogen to nitrogen triple bond. Nitrogen to nitrogen triple bond. 946. 946. Nitrogen to nitrogen triple bond. 946. Hydrogen to bromine single bond. Hydrogen to bromine single bond. That means H to Br single bond. 364. Oxygen to oxygen double bond. 498. 498. Have you given oxygen to oxygen single bond?
Yes.
Oxygen to oxygen single bond?
No.
Only the oxygen single bond. 142. 142. Fluorine to fluorine, that means fluorine in fluorine molecule now. Fluorine to fluorine, 159. 159. Samuel and Co there. Chlorine to chlorine, single bond. 243. 243. Bromine to bromine, 193. Iodine to iodine, 151. 151. Iodine to iodine, 151. Okay, we stop it there. We have more, any form of covalence, but I believe that majority of the things that we're going to be working around will actually be based on these ones. If we are to talk about bond angle, bond energy. Are you get what I'm saying now? Are you with me? Now, before we go on further into the calculation, let's state a particular law which is very important for us to understand the concept of this. A's law. A's law. Is this restaurant? The Ace law. What's this law talking about? Ace law is talking about that so far that heat energy, this energy, enthalpy, is actually a state function of a particular what do you call particular chemical system. It's a state function. That means it's not dependent on the pathway. Rather, whatever that we have initially and what we have finally. Are you get what I'm saying now? It's saying that we can actually associate this particular heat that is being involved with a particular reaction or heat change, looking at the summation of the initial, which is the reactant heat, and the final heat of the product, irrespective of the pathway of the reaction. That means we are not taking into consideration the pathway of the reaction. Either it occur in a step, 2 step, 3 step, or several steps before getting to the final point. What is saying that it's only depending on the heat of the reactant and the heat of the final product. And the heat of the what? Final product. So now let's write. Ace law. Ace law states that Ace law states that the heat involved during a chemical reaction is the summation, we call it heat of summation too, of the heat of the reaction CL2 to give CCl4 plus ACl4. These particular ones, this is gas, this is a gas, this is gas, and this is likely what? It's just vapor form. Are you getting what I'm saying now? Do you understand what I'm saying? What we are saying here is that this particular reaction is happening straightforward this way. The heat that is actually involved in this reaction is independent of, it's going to be the same thing as when you depict this particular reaction in stages. How it occur of Cl2, this is stage 1, to give CH3Cl plus ACl. This is stage 1. Then the stage 2, this one again, CH3Cl plus another Cl2, Abi, to form what? CH2Cl2 plus ACl. This is stage 2. Do you get me now? Then we have CH2Cl2 plus Cl2 to give what? CHCl3 plus what? ACl. This is stage 3. Then we have CHCl3 plus Cl2 to give what? CCl4 plus ACl. This is stage 4. We are saying that Getting to this particular final product from here towards here and depicting it like this to go on to this particular point, the heat that is involved is independent of this particular stage. Not that we have, because we have several stages here, that the heat of what do you call it, the heat involved will now be different or greater or lesser than the one that we have for this one directly. The total heat here, sum it together, it will be equivalent to the heat that is involved in the direct reaction. So this is a direct pathway. This is what? Indirect pathway, going through different stages. Remember, the catalyst here is your UV. Do you get it now? Do you get it? There are certain, what do you say? You did not get it. What exactly did not get it? I got these ones. And this is how the reaction occurs. Look at it. It's a substitution reaction in organic chemistry. This particular one substitutes for hydrogen that is here. This is saturated hydrocarbon. So in saturation, we don't undergo addition, rather we undergo substitution. So what happens is that this Cl, one of these Cl, substitute for H here, while the other is combined with the other Cl. So we have CH3Cl. Instead of CH4, it has reduced to 3. And the other H that makes it 4 here, combined with the other Cl here. How many Cl do you have here? 1, 2. How many do you have here? 2. How many hydrogen do you have here? 1 plus 3. 4. How many do you have here? 4. What's carbon? So same thing happens subsequently. Do you get it now? It's a substitution reaction that occurs in a gradual process. So now, what is now the whole thing? If you sum up all these equations together, you will get this one as the final one. What do we mean? Look at it. At this reactant side, we have this, we have this. So this can cancel this, yes or no? This is in product, this is in reactant, having. This one we cancel this. This we cancel this. What we now have left? We have 1, 2, 3, 4. How many do you have? It's not 4. Then we have CH4. This is not CH4. What we have at this side? This, remember, this has cancelled this. This has cancelled. This has cancelled it. So it remains this one, I mean, plus how many of this? 1, 2, 3, 4. How many do you have here? 4. That is how it is. So that is what we call A's law, and it's actually helping us to understand fully well that when we have a reaction occur in several stages, we can actually bring back all of them by summing up those particular what we call it, heat change in every of the reaction together to acquire the final what, heat change. Do you get the concept now? So that is that. Any question before we move on? Any question before we move on? I would like us, maybe we take 1 or 2 questions on heat change, but I want us to treat entropy and gives free energy first, or what we call the free gives energy, or we call the free energy. Do you want to take question on this first? Do you want to take question on this first? Okay. Okay, please open. Okay, please, if you have a past question, please check past question and let's see if we have 1 or 2 questions pertaining to UV, ultraviolet. So that's the meaning of UV there. Drink. But don't become a drunkard in process. Although you are a drunkard already. But
This one is very active.
Yo, no, it's not what I'm thinking. This one you're saying that water is very active. Hope it is water that you are still drinking, and it's not another thing.
It's very active.
Okay, please let's take this question down.
Wow, this guy. How do you learn? How do you learn? This is my common sense. They do like this.
Okay, is it the same formula I gave to you last week concerning heat of combustion? Is that what side that person is asking for today? That is external. We have talked about that is in molar mass, per molar mass. Yes or no? So it does already make mention of. It does. No. It's under heat of combustion. We talk about bomb calorimeter. Now read. I said read. Is it read or write?
No, I stop my good that they how do you learn? It makes sense now.
How much heat? How much heat will be liberated? Let's write, please. How much heat will be liberated if 10 grams of hydrogen burns in excessive oxygen? How much heat will be liberated if 10 grams of hydrogen burns in excessive oxygen? According to the following equation, oxygen, according to the following equation, H2 when there is no fan here, why won't I sweat? Now, I can write it in two ways by actually giving the change in heat energy here. I get what I'm saying now? By actually giving change in heat energy here, or I will allow us to calculate it using the bond angle, bond energy. I get what I'm saying now? We can calculate it using the what? Bond what? Energy. So how we depict it? Let me put that one so that we can understand bond energy better too before we continue with this solution. I get what I'm saying?
Yes, sir.
Now look at it here. 10 gram of what?
10 grams of
Hydro. 10 gram of hydrogen. Okay. Now look at this place here. The heat that will be involved here. This one, it can be restructured in terms of structural formula. We can draw it this way. Yes or no?
Yeah.
Is that not the meaning? So this one gas plus half of O to O. Yes or no? To give what? OH. Yes or no? And this one is also what? Gas. So what happened here? We have it that H minus H to H, not H minus H, plus half of what? O to what? O. Yes or no? Then minus bracket, Abi. O to what? H. Abi, how many do you have here? 2. Yes or no? Yes or no?
Yes, sir.
So that is your what? Change in what? Heat. Bond of reactor minus what? Bond of reactor minus what? We want bond of reactant. This is summation of bond of reactant minus bond of what? This is this. OH, OH. Yes or no?
Yes.
How many OH do we have there now? Do you get that now?
Yes, sir.
What is it? No, Azar. I got this. Oh, I got this. I got this. Is this not H2O?
Not down.
Which one? Oh. And this is OH. Wait, I will answer everybody one by one. This is OH here. This is OH. 1, 2. How many do you have? OH, O to H, or H to O. Any how you want to put it? We are doing calculation now. No, not 2 oxygen and 2 hydrogen. No. This is bond. This is about bond, not about atom. Not about what? What you want to do is that about atom. That is not what we are calculating there. We are going to substitute for OH here, which is the bond energy, not OH as what we call it as a radical. Do you get that now? We are talking about O form a bond with hydrogen and form a bond with another hydrogen. How many of that we have? We have 1, then 2. Do you get that now? Another person with another question there? I've answered it. Okay. Do you get that now? If you have a question at the back there, you better speak up now or remain silent forever. Yes? How do I get this too? I said we have bond. How many OH bond do we have here? 1, 2. Yes or no? That is why we are having 2 for here. Yes? Oxygen form bond. How many OH bond do we have inside this place? That is what we have here. It's not about splitting. This is not atom. This is bond. This is what? Bond. If it is C to C double bond like this, you don't split it that is C, then C. No. This double bond exists between these two. That means at a time, at a single point, they actually interacted together this way. By the development of the orbital. Do you get that now? So that is it. So it's different. And as we say that 2 here doesn't mean that we have 2 oxygen, 2 hydrogen. No, that is atom. That is not what we are doing here. I get what I'm saying now? That's not what we are doing here. So from there, according to your notes, What do we have? H2H here. What do we have there? 436 plus 1/2 of what? Then minus what's there? This one, OH. Hydrogen to oxygen.
He didn't give us that. He's not giving. Oh, no, why? Don't give it.
In fact, I gave it to you now. H2O 464 464. Not can hydrogen form double covalent bond? No. Why? Or do you don't know the meaning of covalent bond, that particular single covalent bond? Do you know the meaning of that particular single covalent bond you are seeing? We are talking about a pair of electrons. An hydrogen exists, its own electron exists in K shell, and K can only take maximum of what? So it cannot be more than one covalent bond that it can form. Do you get that now? Okay. So we have what? 464. Now let us do this. This plus this is what? 436, Abi? This multiplied by this is what? 1 what? You are saying 1 to 1. You are smoking. 7 what? 71 minus whatever we have here. 2 multiplied by this is what? 2 multiplied by this? 9 2 what? 8, right? This plus this is what? 5 what? 507 minus what? That's equal to what? Minus 4 to 1. Now listen to me. This particular one is given based on the source of this particular OH. I'm saying in other sources it might be higher than this. I don't say now. It might be what? Higher than this. So that's it. Can I clean? This one here. Which one? This one? Everything in the reactant is what we added together. That's what we add there. Then this one is the product. We said that BR minus BP. Is that not the question we gave? So can we move on now? Can we move on now? Can we move on now? Okay. So we have 421. This is kilojoule per mole. Yes or no? Yes or no? Yeah. Kilojoule per what? For 1 mole, this is the change in this. Yes or no? Now we are now making reference to hydrogen as the one that is combusting there. They are going to give you in JAMB most likely they will not give you anything pertaining to bond angle. I gonna say bond energy. Rather they will state the change in energy straightforward. I'm still going to do that now. I gonna say sometimes what you call in JAMB it will be stated here instead of giving 421 kilojoule per mole, it can be given at 456 kilojoule per mole. I get what I'm saying now. It will be given as for the change in this particular energy. I get what I'm saying now. Okay. So what if this one is for 1 mole? If this is for 1 mole, what will now be for 10 gram? Now they are asking of 10 gram of what? Hydrogen gas, Abi? Is that not it? So what is the gram? What is one mole of H2 gas? Is what? 1 mole is what? Is not equal to H plus H, which is equal to what? 1 plus 1, which is equal to what? 2 gram. Yes or no? That means 2 gram per mole. Yes or no? Yes or no? So how many mole is 10 gram? That is 10 gram. We have 10 gram in mole will be equal to what? Mass over what? What's it I don't understand? From west side 2 gram. What is hydrogen gas? Is it not H2? What is hydrogen? What's the mass of hydrogen atom? 1 gram. So that is what we added together. So we have mass. What is the mass? 10 gram. 10 gram over what molar mass? 2. So what will that be if you divide? 5 what? Mole. Yes or no? The gram will have cancelled gram. Then this per mole that is here will come up to become mole. Abi? Yes or no? They are asking us what's the energy associated when this particular 10 gram of this combust. That will be equal to what? Minus 421 kilojoule per mole. That is over mole, Abi? Multiplied by what? 5 mole. Mole cancel what? Mole. 5 times minus 421 is what? 2105 kilojoule. No kilojoule, not kilojoule per mole, kilojoule. Please minus, sorry. The minus is indicating what? That's what? It's giving out exothermic. Exothermic that it is what? Giving. Oh. Do you get the concept now?
Yeah.
Demilade, are you confused? Speak up now, you remain silent forever. Huh? Yes, Aisha. Okay. So, but if you are given, now let's talk about this instance now. If you are given this, let me read a particular question. Just same thing. Let me find it out here. Now, if you are given heat of combustion, if you are given heat of combustion of this H2 to be minus 286 kilojoule, if you are given heat of combustion to be minus 286 kilojoule, minus 286 kilojoule. Minus 286 kilojoule. What will be your standard heat of combustion? What will be your heat of combustion for 10 gram? If you have been given without calculating trace law and through bond energy, are you get what I'm saying now? If you are given as minus 286 kilojoule, what will be your if the heat involved here is minus 286 kilojoule per mole, you are being asked to calculate for this 10 gram. Now they are not telling you to go through this means again. They have given you the heat change there. Do you understand me? Yeah. You don't need to go through this one, just follow this step. Do you understand it? I don't want to know. This is the same question you had before, but this time around you were given this as the heat of combustion. Do you understand? Okay, write the previous question before you now end it. Now add that the heat of combustion of this is this. Abi? Are you looking at me? Are you done? Are you done? Are you done? What's the answer now? Minus what? One what? 143. That's 1,430 kilojoule of energy. Okay. Now write. This is common one in your examination. It's 0.92 gram. 0.92 gram of ethanol is 0.92 gram of ethanol raise the temperature. 0.92 grams of ethanol raise the temperature of 100 gram of water from 298 Kelvin. 0.92 gram of ethanol raise the temperature of water of 100 gram of water from 298 Kelvin to 312 Kelvin, 312.3 Kelvin, sorry, 312.3 Kelvin. When burned completely, what is the heat of combustion of ethanol? What is the heat of combustion of ethanol? What is the heat of combustion of ethanol? Taking the heat capacity of water to be 4,200 joules per kilogram per Kelvin. Or we say that C is equal to 4,200 joules per what? Joules kilogram Kelvin. Minus 1, minus 1. Listen. Okay. From here, if you combust 0.92 what? Gram of what? Ethanol. What's ethanol? What's the formula? C2H5OH. That is ethanol for you. That's the formula for ethanol. So we are saying that you combust this and it give out a particular heat. Because why did you say that give out heat? Because combustion what? Process. Yes or no?
Yes.
They give out heat that we don't know. X. This X heat that it give out is what causes what we call 100 gram of water to be raised from what? To what? 298 Kelvin to what? 312.3 what? Kelvin. So if it raises the temperature to this from here to here, that means this water is what gains this particular heat. Heat gain leads to what? Increase in what? Temperature. Yes or no? Heat gain leads to what? Increase in temperature. Where is that on one from another gas law? It says Charles law. Which voice? It's not any of those ones. It's under kinetic theory of gas. Talking about the average kinetic, what is the temperature is the measure of what? Average kinetic energy of the molecules, and heat gain increase the kinetic energy of the what? Molecule. So therefore their temperature is bound to what? Increase. You get what I'm saying now? Okay. So from here we know that fully well that this one is given in joules per kilogram. So we must convert this one to what? Kilo. So that will be equal to what? 0.1 what? kg. Yes or no? Who doesn't understand we get 0.1 kg? How many gram make 1 kilogram? How many gram make 1 kilogram? So you divide by 1,000. So that's 0.1. So we know fully well that for us to calculate heat is simply change in it is called what? MC what? Change in what? Temperature. Yes or no? So this is now for water. That is M of water, C of water, change in temperature of what? Water. So what is our M of water? 0.1 multiplies capacity, specific capacity of water is what? 4 what? 200 multiplied by what? Change in temperature. That is what? 312.3 minus what? 298. Subtract it. What will be your answer? 14.8. So at that particular point, this 0 will remove one of these decimal. Yes or no? This one remove one decimal. That is 42 multiplied by 143. What's your answer here? 6,006 what? Joules. 6,006 what? Joules. 6,006 what? 6,006 joules. We cannot relate this one yet. This one is not yet in mole. It's not per mole because this is what happens when it's 0.92 gram is being combusted. Yes or no? Yes or no? So we must know what will happen when we combust what? 1 mole of this, even not under standard condition now. Yes or no? We're not talking about under standard condition, but under this same condition, what will 1 mole actually what? Liberate. Are you get what I'm saying now? Do you get what I'm saying? Do you get what I'm saying? 0.92 gram of ethanol was what is combusted, and it gives out this amount of heat. Under this condition, the condition is not stated there. It's not stated if it is standard, if it is not what, if it is substandard condition. Yes or no? But under the same condition, we know that for 1 mole of ethanol, so that we can put it in gram, what you call in dose per what? Mole. Do you understand what I'm saying? If you are still confused, let me see your hands up. Oh yeah, come to the front. Come to the front. Come to the front. Be fast. Pass this place. If you are confused, come to the front. Oh, it's not the way I do this my own calculation. Press your own calculator. If it is this one, press your calculator and get your answer. If it's not the same thing, that's when you should start talking. Press your calculator and get your answer. Okay, what's the problem there?
He said that.
You said that.
I don't understand.
This one. This one.
I said understand what
Yes. How this? What we have done here is based on what you have in your physics. This is from physics here. If you combust this and this raises temperature of water, this particular reaction is exothermic reaction, yes or no? It is being lost from the sea Heat is lost from the sea. So if there is heat loss from the system is equal to heat gain by the water system. Heat loss from what? Ethanol what? Combustion. It's not to heat gain by water system. That's what we have done. And to calculate for heat gain by water system, that means heat of water system must have changed. Change in heat of water is equal to mc theta. What's our m here? It means mass. What this one is specific heat capacity. White theta here is temperature. Please change in it, temperature change. That's how we do it under heat capacity, heat energy in physics. And all these parameters are given, so we can easily calculate for heat change in water, which is the heat gain by what? Water. So what is that? M, mass of water, multiplied by specific capacity of water, which is given as this, multiplied by change in temperature, which is this minus this in Kelvin, to give you what? 14.3. If you multiply this all through, it will give you this. That's what we are talking about. So if this is it, that means that's the heat loss by what? 0.92 gram of what? Yes? How do I? Is given and is constant. Specific capacity is constant for a particular material. For water is 4,200, which can also be rated as 4.2 joules. What do you call it? Kilojoule. I say kilojoule. Joules per what? Can be 4.2 joules per gram per Kelvin. If it is per gram, it can be per gram per Kelvin. 4.2 joules per gram per Kelvin. How is it 4.2 joules per gram per Kelvin? That's what you can do the other time. You might decide to use this, or you convert this one to 4.2. What is the 4,200 joules? What is kilogram? How many gram is kilogram? You know 1,000. So 1,000 gram. Then Kelvin is there. Then this 1,000 we divide it to give you 4.2 joules per what? Gram Kelvin. Why you can write as 4.2 joules gram minus 1 Kelvin minus 1. It can be given this way. It's still the same thing. If you use this the other time, that means you don't have to convert this one to kilogram. Use 100 gram directly. So 100 multiplied by this, multiplied by this, and multiplied by this, it will still give you this. So that is just it. So it is you understanding what you have in your physics also very well. Any other question? Any other question? What's the question? Talk. The person behind you there. Who is behind you there? Sleeping. Please wake him up. Please raise up your yes. That's not all. That's not all. 0.92 gram liberates, what do you call it? 6.6006 joules of energy. For 1 mole of ethanol, what will it liberate? That means C2H5OH will liberate X energy now. So how will we do it? We must look for the mass of this one. This is a molar. This is a mole. 1 mole, abi? So we must look for molar mass of this. So that's 0.92 gram to give 6.006 joules. 6006, abi? So we have this one. 2 carbon is what? 2 times what? 12. Yes or no? Plus 5 times what? 1, abi? Plus bracket 16 plus 1, abi? To give you S. Yes or no? So everything is in gram. 0.92 gram to give you what? 6.6006 joules, abi? 2 times this is what? 24 plus 5 plus what? 17. Yes or no? So give what? X, abi? So 9, that is in gram. 0.92 gram to give you 6006 joules. Then this plus this is what? 46. Is it 46? 46 gram to give you what? X. Yes or no? So we have X equal to 6006 times 46 divided by what? 0.92. So at this particular point here, we can have it that this one, how many decimal places do you have here? 1, 2, abi? Yes or no? That 2 can be taken off and on up with multiply by 100 here. Yes or no? Is that not it? So from here we can have 42 here, 46 here 1, 46 here is what? 2. Yes or no? 2 here 1, 2 here is what? 3003. Yes or no? So 3003 multiplied by 100 what? 300300, and that will be what? Joules per what? Mole. That means for every 1 mole, this will be liberated. So X in kilojoule will be 3. Will now be 1, 2, 3. That is 300.3 kilojoule per mole. Answer. Your dependency on calculator is what makes you to be looking at what are you doing here. You want your calculator all the time, and I've told you several times that your calculator, when you are pressing, if you are so eager to always press your calculator all the time, by the time you press, sometimes you make a mistake in pressing the wrong value in, it will give you a wrong answer. So if your head is not calculating alongside with what you are doing, then you will just record the wrong answer. Funny enough is that your examination, the wrong answer might be there. Sometimes it might not be there. That one will make you to go and reschedule yourself, go and start again. But if it's actually there, speak it and say that they gave me another person's score, they gave me this. They did not give you. You scored that. And that's why some of you come out of the exam and say that and I forgot, I did not know. How come? I pressed this thing now. You did not press this thing. You pressed nonsense. So that is why, to avoid you following up with nonsense, avoid you just recording nonsense without having to actually scrutinize it well, is the reason why it's better you use your head in solving. And you can see, using my head now, is it not easy?
Yes, sir.
It is easy. For me, if I want to write it, instead of going through all this, I will just say 46 here, 1, 46 here, 100. I will say that 46 here is 2. Because I'm not using 46, I'm using 0.46. So 0.46 here will give you 100, 0.46 here will give you 2, then 2 in this one. We get 303. So that I know that this one is already part of my standard form. This particular answer that you're giving in standard form sometime. You already know how it will be in standard form. So having this, you know that it's standard form. So you don't need your calculator from very beginning to the end. Your calculator will just be resting and be looking at you. So that, boss, well done. That's how it is. Any question? Any question? Let's go on to yes. Yes. Okay, talk. How do we get it? Leave this calculation alone. Leave this alone. Press your calculator. If you not get this, then come back. What I'm saying here is that I told you the other time, I said it here, that when I'm dividing this, I know this one is in 2 decimal place. So I can use 0.46 here and 0.46 here. But I know 46 and 92 can interact. Yes or no? Yes or no? So from here, I first take out this decimal point here. So that it will be 92 times 10 raised to power minus 2. That is minus 2 coming up will be 10 raised to power 2. 10 raised to power 2 is 100, Abby. I wrote out 100 here so that this one will remain 92 here. Now you see that that particular decimal place is already cancelled out. Then 46 here, 1, 46 in 92 is 2. Then 2 here is 303. Multiply by 100. Give me this. So that's how it is. Entropy. Are we ready? Entropy. Now, right? Entropy is the degree of disorderliness or randomness of a system. Entropy is the degree of disorderliness or randomness of a system or body. It is the degree of disorderliness, randomness of a body. It can be represented by S. It can be represented by S. S like in soy, in soya milk, in sugar, in salt. I said S can be read by S. Yes, that's what I said. Or is it X that is in soya milk? Okay. Read by S. Full stop. Entropy is actually reckoned under the second law of thermodynamics. The second law is actually reckoned under the second law of thermodynamics, which says that a spontaneous process, occur only if there is an increase. A spontaneous process occur only when there is an increase in the entropy of a system. In the entropy of a system and its surrounding. Say that a spontaneous process occurs only if there is an increase in the entropy. Please raise up your head. Please wake up this person. Yeah, raise up your head. Only when there is an increase, wake up the person beside you there. Blessing. Only when there is an increase in the entropy of a system and its surrounding. What does that mean? What is spontaneous? What a particular reaction is spontaneous? That something is spontaneous. What do you mean? It on its own. That is, it is not aided. It is not supported before it can go through. It happens on its own. It happens on its own. Factors which determine spontaneity. Factors which determine spontaneity of a process. Factors which determine spontaneity of a process. Number one, of a process. Number one, enthalpy. 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 We're talking about each content of the substance, right? Yes or no? Number two. Number two, entropy. S. Entropy. And number three, free energy. Free energy, or the Gibbs energy. Free energy. Full stop. Now let's continue on entropy. Entropy increases from solid to liquid and gases. Entropy increases from solid to liquid and to gases. Yes. For a reversible process, full stop. For a reversible process, at constant temperature, change in entropy is equal to change in heat over temperature. Change in heat or heat over temperature. Change in entropy is equal to change in heat over temperature. Now what do we mean? We are talking about change in S is equal to change in H over what? C. I don't understand now. Such that change in H is equal to what? What do you call it? T delta what? S. Do you get it now? So from here, what's H measured in? Joules, right? What's temperature measured in? Kelvin. So that means the unit for entropy is what? Joules per what? Joules per what? Joules per what? You see where your mind is? Your mind is over there. You know, I'm not seeing you looking at that place. I'm saying something. What was my last statement before now? Okay. Joules per Kelvin. That is the unit there. So you can say that unit for entropy is simply what? Joules per Kelvin. In that we have joules per Kelvin, we can say that change in entropy, which is a standard entropy now, is equal to standard entropy of the product minus standard entropy of the what? Reactant. Standard entropy of the what? Product minus standard entropy of the what? Of the reactant. Now look at this here. In a system where heat is absorbed, the change in what do you call it? Energy will be positive, yes or no? Yes or no? And the temperature we use to divide. That means at that particular point, entropy of the product will be greater than the entropy of the what? Reactant. But in a system where change in energy is negative, the mean entropy of the reactant will be greater than the entropy of the what? Why? Because as they lose energy to the environment, kinetic energy of the system what? Drops. So degree of randomness what? Drops. Do you get it now? Do you get that? That is what is about entropy. Let's move on. Gives free energy. I want to call it free energy. The free energy of a system is the energy which is available. The free energy of a system is the energy which is available for doing work in the system. Is the energy available for doing work in the system. Full stop. Hence, it is the driving force that brings about chemical reaction. It is the driving force that brings about chemical reaction. Standard free energy G standard free energy is a state function. Standard free energy is a state function. Standard free energy is a state function, not state and capital. What are the woman here? Who is here? Standard free energy is a free state function. So you can write change in standard free energy is equal to change in standard free energy of the product minus change in standard free energy of what? Reactant. Change in standard free energy, because I'm pointing there now, so people will go and be writing this. This is a free energy. Changing this is equal to changing is equal to what do you call it? Free energy of product minus free energy of what? Reactant. Write that down. Now, paragraph. For a change at constant temperature. For a change at constant temperature. For a change at constant temperature, we have it that for change at constant temperature, we have it that G, delta G is equal to H standard minus change in S. H standard minus what? C what? Change in what? S. But if it is now changing Gibbs free energy, it will now be changing it minus C what? Sorry, changing what? S. What is this? When I'm talking about Gibbs free energy, say that energy that is available to do what? There is a total energy, internal energy of the system, H, minus the one that will be taken off as a result of the situation of the body, as a result of the state of that particular what? Body. Are you gonna understand now? So that is what we are talking about here. So the remaining energy that is now left is the one that's available to do what? And once that one is available, then that means that particular, but the more the free energy is available, the more the reaction, the more that particular body will be able to, that particular system will be able to go undergo reaction on its own. On its what? Own. If the change in giving the Gibbs energy of a system is equivalent to the activation energy, reaction will be spontaneous. Remember, the activation energy is energy required, Abby? For what? To what? To occur. To proceed. Yes or no? Yes. It must be reached. That barrier must be broken for a chemical reaction to what? To proceed. Are you with me now? So now let's look at certain conditions that are very important. Go. Let's look at certain conditions here that are very important.
Let's look at that.
Effects of changing Gibbs energy on a reaction process. Effects of changing what? Effect of changing Gibbs energy on a reaction process. Change in Gibbs energy on a reaction process. Number one, when change in Gibbs when delta G, that is delta G Nabi, when change in Gibbs, or write delta G, when delta G is negative, the reaction is spontaneous or feasible. The reaction is spontaneous or feasible. The reaction is what? Spontaneous or what? Feasible. When change in G, feasible. That means it can go through. Feasible. Feasible. Not visible. Feasible. Not visible. Feasible. The reaction is feasible. Number two, when delta G is positive, when delta G is positive, the reaction is not spontaneous. The reaction is not spontaneous. Okay, the reaction is not spontaneous unless the resultant effect of both H and S leads to net decrease in G. Unless unless the resultant effect of changing changing enthalpy, that is changing H, delta H. I'm just rephrasing it so that you want to write it. You are not in primary school, you must write this word for word. Change in H and S, that means change in entropy, leads to net decrease. Leads to net decrease. Leads to net decrease in delta G or in G. Lead to net decrease in Gibbs energy. Number three, when change in Gibbs or delta G is 0, the system is in equilibrium. The system is in equilibrium. When change in Gibbs or delta G equals to 0, the reaction, the system or reaction system is in equilibrium. That system is in equilibrium. Do you understand that now? What are we saying? Now listen to me here. What is actually reactant? It's not reactant. It's not reactant. It is the activity of the reactant that will bring about chemical reaction. Yes or no? Yes or no? We now say that when delta G is negative, that the reaction is what? Spontaneous. That means the reaction will occur on its own. What do we mean by that? Delta G itself is equal to G of product minus G of what? Of G of what? Reactant. Yes or no? For this to be negative, that means this is greater than this. Yes or no? That means the reactants have what? Greater what? G value, or gives what? Energy. Gives what? Energy than the product. So we say that at that particular point, the reactant will actually undergo a reaction in a spontaneous manner. That means without being aided. But when delta G is positive, that means for the for the delta G that is positive, that means that of gives of free energy of the product is greater than that of what? The reactant. Is greater than that of the what? The reactant. If it is greater than that of the reactant, that means we have less energy at the reactant end to actually proceed the reaction. So the reaction will have to be assisted by adding either heat to the system, are you gonna say now, or adding any form of energy to allow the system to go through. Are you gonna say now? And if you cannot add heat or energy to the system, what can you do to actually make the reaction to go through? You will lose activation energy. What do you use to lower the activation energy? Catalyst. So you can catalyze it. So the catalyst can be any form of chemical catalyst or by what? Heat as a catalyst. And if the heat is at the gamma what? Catalyzed reaction. Do you get the concept now? But when delta G is equal to 0, that means both the reactant and the product have the same Gibbs energy. They have the same equal free what? Energy. Such reaction is said to be at equilibrium. Such reaction is said to be what? At equilibrium. That means the rate of forward reaction is equivalent to the rate of what? Backward reaction. That's what we are talking about. Any question about that now? Any question about that? Any question about that? Your discussion with your friend will not help you. Ask me question. Any question about that? Okay. Now let's take this question down. Right, Amina. Here is up here. I will use it too. And I'm not using it so that you are not hearing me well. So no problem. Amina, raise up your head. The person beside Gigi. Look at the person beside you. If anybody is sleeping beside you and you are not waking that person up, then you are not in this class with us too. I mean, you that's beside that person, you are not in this class with us too. The reaction is carried out at a temperature of 57 degrees Celsius. The reaction is carried out at a temperature of 57 degrees Celsius. Full stop. Degrees Celsius. If the enthalpy change is minus 500 joules, if the enthalpy change is minus 500 joules, and the entropy change is plus 15 joules, minus 500 joules, and the entropy change is plus 15 joules. I said 500 joules, sorry, it's 5,000 joules, sorry, not 500 joules. 5,000 joules minus 5,000 joules, sorry. Change that from 500 to 5,000. Calculate the free energy change of the reaction. Calculate the free energy change of the reaction. Calculate the free energy change of a reaction. Calculate the free energy change of a reaction. Calculate the free energy change of the reaction. How do you do that? We have our formula there already. Yes? Yes or no? Look at the board here. Look at the board. Tell your friends at the back to look at the board. We are asked to look for free energy change. We remember the formula. Delta G is equal to what? Delta H minus what? C what? Delta what? S. Yes or no? Yes or no?
Yes, sir.
Okay, from the question, we are given delta H to be what? Minus 5,000 what? Joules. Yes or no?
Yes.
Why our T is equal to what? 57 degrees.
Yes.
You convert this one to Kelvin to be 57 plus what? 273. That is what? That is what? 33 what? 0 Abby? Kelvin. Yes or no?
Yes.
Then our delta S is what? Delta S is what? Is it minus 15? 15 what? Joules per what? Kelvin. Yes or no? Yes or no? Very good. So impute that one into our formula. Our delta G will be equal to what? Delta H is what? Minus 5,000 minus bracket. What's our T? 330 multiplied by what? 15. So our delta G will be equal to what? Minus 5,000 minus 330 multiplied by 15. 15 times 0 is what? 15 times 3 is what? 45, Abi. Keep what? 4. 15 times 3 is what? 45 plus 4 is what? 49. So that is 4950. Our delta G will be equal to this plus this. 4 plus 5 is what? This is minus, Abi. That's minus. So 4 plus 5 is what? 9950. What is that? Joules. Answer. Oh yeah, madam, stand up. Stand up, stand up. Oh yeah, stand up. Be fast. Oh yeah, stand up. Peculiar. Stand up, stand up. On your feet. Peculiar, stand up. Wake up this woman. Madam, oh yeah, stand up. Stand up. On your feet.
Alright. So this is just a summary note.
Peculiar, yeah? On your feet. Be fast. Yeah, madam. I'm not negotiating with the three of you. Stand up, stand up. Stand up. Okay? This one I just writing. Stand up. Oh, yeah? Three of you, stand up, be fast. Stand up, just stand up on your feet there. Stay there. Oh, yeah, Mary Jane, stand up, be fast. No, she's not sleeping when I was coming. Yeah, stand up, stand up. That sleep will not leave you until you stand. Oh yeah, Mary Jane, stand up now. You want the game for Gavin? You want? Okay. Any question about this? Any question about this? Okay. We are moving on to our topic 2. Topic 2. Rate of chemical reaction. Rate of chemical. You said that since as well. Who is delaying the class? Am I the one delaying?
No, the time is slow.
This time is slow. Rate of chemical reaction. Rate of chemical reaction. Are we ready?
Yes, sir.
What's the problem? It has nothing. Eh? Rate of chemical reaction. What do you mean by rate of chemical reaction? Whenever you hear the word rate, your mind should go to per time in reference to what? Time. Rate of doing work per time. Rate of chemical reaction. How chemical reaction occur in relation to what? Time. I don't understand now. That means the pace at which the speed of a chemical reaction, the speed at which work is being done is what we call power. Yes or no? Yes or no? So also the speed at which a chemical reaction occurs is the rate of the chemical reaction. Okay, ask from your friend there. So when we're talking about this, we are simply talking about in terms of reactants going on to products, which can be A going on to B, or better still when A combines with B to form C plus D. So in this wise, the rate at which a reactant is being used up to form a product is the rate of the reaction. That is in terms of the reactant. In terms of the product, the rate at which a product is being what? Formed. The rate at which the reactant is being used up, because it's what will be used up to form a product, while the rate at which the product is being formed in terms of product. If you are defining rate of reaction in terms of product, rate at which the product is being what? Formed. Or the amount of a reactant used up per seconds or per time. Or we say that the amount of product being formed per what? Time. The amount of product being formed per time. The amount of product being formed per time. If the it's not working. Okay. If the product is actually gas, the amount of the product, we can talk about it being liberated, because gases are usually being what? Liberated, giving off. Giving what? Off. The amount of product liberated per time is simply the measure of the rate of that particular reaction. It's measure of the what? Rate of that particular reaction. So sometimes we might talk about this amount in terms of weight, in terms of mass, sorry. In terms of mass, we can talk about it in terms of mole, we can talk about it in terms of volume. We can talk about it in terms of what? Volume. That is, in either way, we are making it in reference or as a ratio to what? Time. As a ratio to what? Time. Are you gonna say now? As a ratio to what? Time. Let me write on the board for the sake of people online. Per time. So what we are saying? We said I change a rate of reaction is equal to amount of reactant used on over what? Time taken for this particular reactant to be used. I gonna say now, or we can put it also equal to amount of product formed over what? Total time taken. Over total time taken. That is what we call the rate of a chemical reaction. Now, depending on what we are measuring, either in terms of mass, or in terms of mole, or in terms of volume, that's what will now determine the unit. So, in terms of mass, the unit will now be mass over what? Seconds, which is what? In mass, it should be what? Gram per seconds. That's the unit there. The charger. Go and ask Mr. Ladison. Okay. So we have what do you call it? In terms of molar mass, we have it as gram per mole over seconds. So that will be what? G mol minus 1 seconds minus 1. Are you gonna say now? In terms of concentration, we can have it in mole per dm cube over seconds. That is a mole dm cube minus 3s minus 1. Or if it is in terms of gram per dm cube over seconds, is gram dm cube raised by minus 3 minus 1. So, in terms of volume, we can have it in dm cube. Sir? Yes?
Come and see your children. All those times.
All of you sleeping, stand up.
Okay, so
nobody is sleeping. Okay, dm cube per seconds, which can be dm cube seconds minus 1, and it can also be cm cube per seconds, depending. That's cm cube second minus 1. Any of these, depending on the situation, can make up your unit. Can make up your what? Unit. So please look at all this and flow with them. Okay. Is it working? So for me, please come and sit down. Before Abi. Now let's quickly take this small question down. When is 0.46,
Yes, sir.
when is 0.46 gram, when is 0.46 gram of calcium triazocarbonate, when is 0.46 gram let's use 0. Okay, let's use that one. When 0.46 gram, hey, Mulumbu, sit down. Mulumbu, sit down now. If you are not Mulumbu, stay, oh, just sit down. If you know you are not Mulumbu, don't sit down. So all of them agree that they are Mulumbu. When 0.46 gram of calcium CaCO3 was added to excess dilute hydrochloric acid HCl, carbon 4 oxide was evolved. The complete reaction took 5 minutes. What is the rate of the reaction? What is the rate of the reaction? Now take note of something here. For you to calculate rate of a reaction, when two properties are reacting together in a system, what will determine the rate of reaction is the limiting reactant. Is the what? Limiting what? Again, is the what? Again, is what? Is the limiting reactant. What do you mean by limiting reactant? The reactant that is not enough, that is less in terms of molar comparison for stoichiometric reaction, is what we call the limiting reactant. What do we mean by that? Remember that whenever we have a complete equation, CaCO3 now as our equation here, solid reacting with what? HCl, which is what? In aqueous form, to form what? CaO, Abi? Yes or no? CaO plus what? To give you a CaCl2, which is what? This is soluble, right? Plus what? H2O liquid plus what? CO2 gas. That is the characteristics of reaction of acid with what? Triazocarbon. With triazocarbon. Okay. In this wise here, we say that these two are reacting. This reaction is not yet balanced. Is it balanced yet? Is it balanced yet? So what's the balancing of this reaction? 2 here. Yes or no? Any other thing? Is it balanced now? Very good. Now that means for every 1 mole of this, we acquire 2 moles of what? HCl for the reaction to be what? To occur, to complete. Yes or no?
Yes,
to react completely. For every 1 mole of this, it will require 2 mole of this for complete reaction to what? Occur. So in this wise, that means if we are given a certain amount of this, if this one is not double of the mole of that particular amount that is given here, that means the reaction is not what occurring what completely. That means at that time the one that is not making it to occur completely is the limiting what reactant. Is the limiting what? Now if we have more than 2 moles of HCl present, if we have more than 2 moles of HCl present and we have 1 mole of this present, the limiting reactant is no more HCl, it's now this one. Why? Because this one will react and this one will still have left O, because 2 moles out of this will react and the remaining ones will be all reacted. So now looking at the question, which one is now the limiting reactant? We said that was added to excess. Emphasis on what? What's the meaning of excess? Too much. So what's now the limiting reactant here now? Which one is not the limiting reactant now? Calcium what? Calcium triazole is the limiting reactant. Very good. So that means, according to my statement the other time, CaCO3, which is limiting reactant, will now be the one that will determine the rate of what? The chemical reaction. Because it's the one that can be used up. This one is not what? Used up. Remember that I said that amount of reactant what? Used or used what? Up. Do you get it now? Amount of reactant used up or product what? Formed. Do you get it now? So out of all here, we're not giving any parameter about the product. Are you understand now? Only that they just mentioned carbon dioxide, but we give parameter about one of the reactant, which is the limiting reactant. So that one is what we use in calculating the rate of what? Chemical reaction. So the rate of chemical reaction now will be equal to what? Amount of what? Ca, what's the reactant? It's not CaCO3. CO3 what? Used up, Abby. Over what? Time what? Taken, Abby. What's the amount of CaCO3 used up? 0.46 gram, Abby. Over what? Time taken is what? 5 minutes. Is it our what do you call it? Unit? Is it in gram per minute? Gram per what? So we convert minutes to seconds. That is 5 times what? Yes or no? And that is equal to what? 0.46 gram over what? 3 what? 300 what? Seconds. So that one will give you what? Is 0.00046 divided by 3 gram per seconds. So what will that be? That will be 0.000. 3 in 4 is what? 1, Abby. Remainder 1. In 16, 5. Remainder 1. In 10, 3. Abby. In 10, 3. Yes or no? In 10 again, 3. In 10, 3. Recall. So that will be equal to what? That will be equal to what? Oh, is it 0.00? And you put it not up. 0.00. Okay, so at that particular point, recall, Abby, That is, we can put 1, 2, 3 dots. That means this 3 is what is reoccurring. Abi? So that will be what? 1, 2, 3. 1.5 3 times 10 raised power 1, 2, 3 minus 3 gram per what? Seconds. If you don't understand that, press your calculator. Press your calculator. If you don't understand that, press your calculator. Because the calculator is what you want to use to determine if it is right or wrong. So press it. And when it is wrong, call my attention. Yeah. When it is wrong, call my attention. Subtopic, yes? Okiki? She's not writing. Okiki? You are lost, Kaza. Better go and find yourself somewhere. Now, subtopic. Waste. Assuming we are given a certain unit to actually calculate it, maybe you have to calculate in what do you call it, mole per seconds now. Then you must look at the equivalence of 0.46 in mole for this, and that's mass, which is this over the molar mass of CO3. By the time you determine that, it's what you are going to bring here over 5 times 60 seconds, and you still get your answer. Anyway, it's funny you are smiling. That's how we take you away. I'm telling you now. We are never fighting. You are the one fighting. I'm not fighting. Stop that. Stop that, Joe. The writing pen on somebody's face. It's not good on the body now. Ọ̀rẹ́ kò fún ẹ níyàwó yẹ̀wò náà gbèdé gbé. Ways of measuring reaction rate. Ways of measuring reaction rate. Way of measuring reaction rate. Are we there? Number 1. Mass of the reaction system. Mass of the reaction system. That is change in mass. Mass of the reaction system. Mass of reactant used up or mass of product what formed. Are you gonna say now? Mass of the reaction system. Number 2. Volume of gaseous product. Volume of gaseous product or volume of gaseous substance, either for the reactant or what product too. Volume of gaseous substance. Number 3, amount of precipitate formed. Amount of precipitate formed. Amount of precipitate formed. Amount of precipitate formed. Sorry. You are smiling there. I don't know what he's telling you that makes you to be smiling. You, two of you, you are looking at the back now. You yourself, you know yourself. This one that is telling you something, you are smiling. No fully well. Kirikiri is not far from Ikorodu. Okay. Amount of precipitate formed. Number 4. Change in color intensity. Change in color intensity. Change in color intensity. Remember doing your titration process when there is change in that system. That's that it has occurred. You know, stop. Time you stop it there. That's the same thing. Some of you say that you should shake beaker. You should check your conical flask. Instead of checking it, is your bumper that will be shaking. This one will be staying at one point, but this your bumper will be going to travel. What are you shaking? Shake the beaker and let's see. If you want to shake your body, go to what? Dance floor and go and do that. Nothing. Change in pH. Change in pH. Change in pH. And number 6, if there is gas product formed, then there can be change in gas pressure of the system. Change in what? Gas pressure. Change in gas pressure, total gas pressure. Change in total gas pressure. Change in total gas pressure. Change in total gas pressure. No, number 78. Number 6. Okay. Change in total gas pressure. That's that. Rate curve. Rate curve. Rate curve. R-A-T-E curve. C-U-R-V subbomb subtopic. Rate curve. Subtopic. Rate curve. Don't worry, by 12:15. You don't need to ask for time. No. I'm not the one who wasted time. I said it the other time. I'm not the one wasting your time. I'm only waiting for the setup. And let me have the setup like this. Objection overruled. Mr. Shiju, they said they will kill me if I continue the class after 12. Some of them are already bringing out gun. Thank God I have bulletproof. I just want to ask for permission. I said till 12:15 we are going to stop. By 12:15 I said 12:12. Okay, 12:50. Okay, now rate curve. Are we there? Let's write rate curve. Don't worry, it's for your own benefit. Examination is approaching. We have less time to actually cover up things. Okay, rate curve. This is the graphical representation. This is the graphical representation of the rate of a reaction. Of the rate of a reaction. This is the graphical representation of the rate of a reaction. Of the rate of a reaction. The slope. The slope. The slope of a rate curve is the measure of the rate of the reaction. Is the measure of the rate of reaction. No, be looking at it. Is the measure of the rate of the reaction. Full stop. Paragraph. The steeper, steep. Ma, you are wait before you draw. Right. The steeper the slope, the higher the rate of reaction. The steeper the slope, the higher the rate of what? Reaction. Continuous reaction point. So this steep point. This particular one is continuous reaction point from all this particular region. Hey, as you get to this particular point, it sees that the reactant has been either used up or the maximum amount of product has been what? Formed. Are you gonna say now? And at that particular point, time will keep on going and there will not be increase in the amount either used up or what? Or formed. Are you gonna say now? That is the concept there. That's the concept there. Keno, if they let me put camera so that you can see. Are you getting what I'm saying now? So that is it. Now let's write features of the rate curve. There we go. Want to draw? Okay, quickly draw. Or let me dictate and then you draw later. Features of rate curve. Features of rate curve. Number one. Features. No, features. Okay, features. Number one. It passes through the origin. It passes through the origin. Not origin as drink. It passes through the origin. Number one, it passes through one mass at the start of the reaction because there is no change in concentration or mass at the start of reaction, not Catholic mass. Okay. Mass. It's steep at first. It's steep at first. That is,
That is,
rate is faster at the beginning. That is, rate is faster at the beginning. Rate is faster at the beginning. Number 3, it becomes less steep later. It becomes less steep later. It becomes less steep later. Less steep later. This is because slow down. This is because the rate slow down. Number 4, it finally become horizontal. It finally become horizontal with the time unit. It finally become horizontal with time unit. That is, the reaction reach the end point. 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 So with this point of mind, I hope I've been able to what? Who am I to convince you? Thank you so much.